Now this illustration deals with motor and motor control circuits in accordance with 240.4G and table 240.4G. Now the boxed in information to the left, let's look at sizing the overcurrent device using a circuit breaker. Step 1, we're instructed first to review 430.6A1, which for three-phase motors refers you to our table 430.250. And we would pick up for that 50 horse, 208 volt, three-phase motor under that column that is 240 volt, 208, etc. listed there. We'd pick up 143 amps. Now, step 2, we would refer now from using table 430.250, or excuse me, table 430.52 and section 430.52C1. The minimum percentage selected from that table for an inverse time circuit breaker using the 4 selection steps of what type of motor is it. Well, let's say it's an induction type squirrel cage motor. 2, what is the voltage that we would have, and is it single phase or three phase? You'd say, well, it's three phase. 3, what size device are we using, or what type, better stated, inverse time. Number 4, then what is the percentage? That's the 4 things we look at using the table. Step 2, 250%. And we select that and apply the math of step 3. 250% of 143 amps from step 1 would be 357.5. Now you have to make a decision. Do I want to stick with 430.52C1? That says in that section you can't exceed the percentages of the table. So the percentage of the tables was, produced a current of 357.5 amp. So you round down to 350, which is the next size device below the 357.5 as listed in 240.6A, which refers you to the sizing of the device, table 240.6A. So the solution and the answer for the inverse time circuit breaker is a minimum 350. But now let me point out that if you could use a smaller size circuit breaker and start and run the motor, that'd be okay. The table just gives you a percentage to start with to select your device, and then you could use any size that would start it and run it. The code does not prohibit that. Now, if you wanted to round up, that's automatic now, but used to you went in steps. You would use the 350 and that would start it, that'd be okay. Now notice, a 350 amp device, typically at 600 volts or less, will hold about 3 times its rating. So when you multiply 350 by 3, you're looking at 1,050 amps that it'll hold based upon its frame size, based upon its voltage, it'll hold for so many seconds. So using that 3 times rule, sometimes the electrician or engineer would just take step 3 and just round that up to an even unit number, and it'd go up to 400, divide that by 3, and they would use a 150 amp device there. Now, that's up to the designer, the installer, and so forth. All I want to point out is that the table just gets you started. You can always drop below. Now, sizing the circuit breaker now, rounding up, step 1, where shows rounding it up. So we could take 357.5 amp Table 240.6a and reference from 240.6a, we could round it up to a 400 amp device. 3 times 400, it basically holds 1200 amps. So the next standard device rounding up is 400, rounding down is 350. And that's what this illustration now is showing for this motor using a circuit breaker. Now on the right, we're using a circuit breaker at maximum size. Then we could use in accordance, since the full load current is say 143 amps, then we would, using the exception 2C to 430.52C1, we could use 300%. If the full load current was below, say, 100 amp or below there, in that value, we could use 400%. But it's greater than 100 amps, so we're stuck with using 300% in the step 2 to the right. 300% of 143 is 429. There is no exception at all in the 430.52 C1 exception 2C, as in car, to round that up. So we'd round down to 400. So a 400 would be max and next size in this case. But if you could round up to 450, or say you had 465 amps, you could round it down, see, to 450. But in the illustration, in step 3, you couldn't round it down, you couldn't round up, say, to 450. You'd have to round down to 400 by the exception 2C to 430.52C1. And in table 240.6C, the round down size device is 400, and as stated, you'd be stuck with that. But now, you don't size these conductors like that. If you did, you couldn't even terminate them in what electricians call the peckerhead. Women in class, or a woman reviewing this, or a girl, viewing this illustration, you know, it'd be the motor cover, and that's just a slang word that electricians use, but if you're a designer electrician, naturally you'd get used to it, so don't take that term wrong as I state it to you. But notice, sizing those conductors, then we would use 430.22. 125% of 143 is 178.8. And when we review 310.14A3, informational note 1.1, which is item 2, as we call it, and selecting the conductor from table 310.16, from the 75-degree column, the 178.8 amp would be 3/0. Even if you selected a THHN from the 90-degree column, since there's no derating or reducing due to adjustment factors or correction factors, then the 3/0 would be selected. And the 3/0 then could terminate to your size protective device, and you could also terminate it under the cover of the motor and connect it to the leads of the motor, and it would, the cover would still go on, and you could secure it to the motor to protect the terminations. Now, you can't oversize it and then try to use duct tape and stuff and makeshift the cover. That's why that the overcurrent device is sized up. Just allow the motor to start and run, and the conductor in the motor then would be protected from the overloads in 430.32 A1 and 2 if you're using the minimum thermal protector overload to start with, or you could use 125% of the nameplate current, size your fuse by rounding down, if the 125% times the nameplate is not a standard size fuse, in accordance with 430.6 A2 and Table 240.6A, you could provide overload protection with fuses instead of a thermal overload. Now, this is what Figure 9-6B states. Now, I know that's a lot of information, but I'm trying to lay this out to the listener or reviewer of this video so that they will fully understand what NEC 240.4G and Table 240.4G allows in conjunction with sizing the overcurrent device and the conductors, supplying the power to the motor, and providing a second stage of protection because we're sizing the overcurrent device greater than 125% of the full load current of the motor based upon the nameplate rating.